welcome back to the video lecture series on pattern recognition. In the last few lectures, we have discussed what clustering is and what are various types of clusterings that can be applied. So, we have as part of this, we have discussed the k-means clustering, k-medoids, then the hierarchical clustering and also the DB scan clustering. So, with examples in the detailed manner we have discussed, and in today's class we discuss one more clustering approach that is based on the graphs. So, based on the graph theory also there is a possibility of applying the clustering, and in today's lecture we will discuss what the graph based clustering is and what are the techniques that are involved in that. So, let us start our discussion. So, in this lecture we will be discussing what graph based clustering algorithms are and so how graph theory can allow us to define the clustering. So, then the various graph construction approaches. So, first of all, to apply the graph based clustering, we should understand how do we construct the graphs given the data. So, there are basically two different methods for graph construction of the graph, that is the k-nearest neighborhood graph and the epsilon neighborhood graph. So, what are the advantages and disadvantages of these two different graph construction approaches? So, once we construct the graph, then we will see how to apply the graph clustering. So, and we will be discussing one of the popular graph based clustering, that is a minimum spanning tree based clustering approach. So, because we are all very much familiar with the minimal spanning tree. So, we will be discussing that MSD based clustering. So, let us see. So, let us start our discussion with the graph based clustering approaches. So, based on the graph theory also allows us to apply the clustering. So, there are a wide variety of methods that are designed based on the graph theory, and we will be discussing them in a detailed manner. So, the basic idea in this graph based clustering is, first of all you need to construct the graph given the data. So, once we construct the graph, so then we can apply the graph based clustering approaches. So, we will see how to apply the graph based clustering. So, to get that graph construction, for the construction of the graph, so the idea here we follow is the nodes, the objects are represented as nodes in the graph. So, we will be given the data objects in the data set, right. So, every object will be represented as a node in the graph. So, the graph could be either a complete graph or it is a connected graph. So, depending on the data that is given to us, either it allows us to construct a complete or the connected graph. So, basically given the set of data objects will be forming the nodes, we assume that they form as nodes in our graph. Say for example, so this is one node, where all these are forming or formed based on the objects, data objects. So, once the nodes are formed in the graph, then we need to identify the edges in the graph, right. So, graph means what? It is a collection of nodes and connected edges. So, where the nodes are connected using the weights or the edges. So, now you need to connect these data objects or the nodes in the graph, and how do we do that? So, based on the similarity measure, say for example, so these two are connected, maybe these two. So, one approach is you just connect every pair of data objects. So, that is one approach, so where that allows us to build a complete graph, but that gives us a complex graph and also it takes a lot of memory and it requires a lot of processing also. To avoid that, what we do is we construct the graph such that it is not a complete graph, and these edges, how these edges are formed is the distance between the data objects. Basically, this is one node and this is the other node of the graph, right. How these nodes are formed? This is the data object 1, data object 2, and what is the distance between these two? So, that distance between the objects will form as the weight of the graph, that is the weight of the edge in the graph. So, say for example, if you consider this edge and if this edge is considered, the weight of this edge is the distance you are computing between these two objects. And what is the distance measure that you need to follow, that is up to you. So, depending on the application or depending on your computational capability, you can choose one of the distance measure, and that distance between this object 1 and object 2. So, that distance between these two will form the weights of the graph. So, that is how basically you are constructing the graph. What is your graph now? All the objects, data objects in your data set will form as a nodes in your graph, will act as a nodes in your graph, and then the distance between these two nodes or a pair of nodes, they form as a weight of that branch or weight of that edge. So, once you have that graph, then you can apply any of the graph based clustering approach. And here the basic idea in the graph based clustering is, if you observe this, so this is represented as a graph. So, of course, the whole thing is represented as a single graph, and these are all the edges between the nodes, right. And the idea here is the distance between the nodes within the or data objects that form a cluster is small, whereas the distance between the nodes or the data objects that are in different clusters is large. So, based on that idea, you need to form your graph, right. So, when you compute the distance or the similarity measure as the edge weight, so how do you need to consider such that, so the nodes that form or that fall in the single cluster, the distance between them should be very small, and the distance between the nodes or objects that fall in different clusters should be very large. So, that is the intra distance between the nodes, the intra distance measure should be very low, and the inter distance means the distance between the objects of different clusters. The inter distance between the clusters, the inter distance measure should be very high. So, that is how we should represent our graph. So, once the graph representation is over, so we can proceed and apply the graph based clustering. But before proceeding, let us see what are the various ways to construct the graphs. There are basically two different approaches for the graph construction, which are the popular approaches. One is the K-nearest neighborhood approach, and the other one is the Epsilon neighborhood approach. Okay. So, now let us see what this KNN and the Epsilon neighborhood approach is. So, how do we construct the graphs? Using these techniques. So, now let us consider these circles are the objects in your data. So, these are all the objects, the data objects in the data. So, these are all the data objects. Now, so I need to understand, so once these are considered as a nodes, each data object is considered as a node in the graph. So, once you have the nodes, you need to form the edges in the graph. How do we form the edges? So, if you consider the edge between every pair of nodes, if you have some 100 nodes, then you will be having 100 square edges. So, which will be tedious for processing, which is very computationally expensive. That is why we do not prefer the complete connection, that is the connection between every node we do not prefer. Instead of that, we define a term called as a neighborhood, and we connect the edges between the neighborhood nodes only. So, we do not consider every node as a neighborhood, right. So, to avoid the computational complexity, and for that we have two different approaches. One is the K-nearest neighborhood and the other one is the Epsilon neighborhood approach. And in case of the K-nearest neighborhood, what do we do is we assume some k value. Remember, this is nothing to do with the k-means, the k value in the k-means clustering. So, in case of the k-means clustering, if k value is 5, then we will be getting 5 different clustering. But the meaning here, the meaning of k here is completely different from the k-means clustering. There is nothing to do with the k-means clustering here, remember that. So, here we assume some k value as 5. If our k value is 5, say for example, if you consider this data object q, so you compute the distance between this object and every other object, and then so you just connect the edges between this object and the closest to 5 objects. Because your k value is 5, you are going to construct the edges between only from one object to 5 other objects. That is how you can reduce the number of connections. That is how you can reduce the computational complexity in the graph. So, that is one way of constructing the graph. So, that is how you can consider the nearest neighborhood. You can define the nearest neighborhood. So, here if you consider this q as an object and you just compute the distance, whatever the distance measure you can consider. So, that q from q to every other object, you just compute the distance measures. So, once you compute the distance measures, you just keep them in descending order, and whichever are close to this q, so you just connect the edges between this q object and the rest of the 5 objects. You need to choose only 5 objects because you have your k value as 5. And again, so for this object I want to find the k edges, the nearest neighborhoods. How do I do that? So, from this object you just find the distance between every other object, and you just connect the edges to the objects which are closest to that object, this object, and you need to only select 5 such objects. Maybe this is close to this and this is the, so only 5 objects I can connect, only 5 edges from every other object instead of having, so 100 edges from every object. If I have 100 objects, this is how I can restrict the number of edges in the graph. Thereby I am reducing the computational complexity of the graph. And now the k nearest neighborhood, if you consider my k value is 3 and this is the resultant graph you can see. So, instead of getting the complete graph, I am getting the sparse graph, so with less number of edges. Because k value is 3, from this I have a maximum of 3. So, here this is one edge and this is another edge. Of course, there is another, it is overlapping. So, you are not, it is not visible. Other than that, there is an edge from here to here. So, there is an edge. So, if you observe here, there are 3 edges. So, from every object if you observe, no, at least 3 edges would be there. Here 3 edges, and here you are seeing more number of edges, because from this object these 3 are close, but from this object these are close. So, that is the reason why we are getting more number of edges associated with that edge, with that node. That is the process to be followed to construct a graph in case of the k nearest neighborhood graph. So, in case of the k nearest neighborhood graph, you are taking a k value, you are predefining that. So, once you predefine that, so you compute for every object, you compute the distance from every other or rest of the objects in the data set, and you just connect that object with the k nearest neighbors. So, that is how the graph can be constructed, and the process is called as k nearest neighborhood graph. And now, let us see the advantage of doing this and the disadvantage of doing this is the k value is simple way to do this, that is the advantage. But the problem here is fixing that k value is very tedious, and you really don't know which is the proper k value. So, that is choosing k value is much challenging here. So, if you take k value like 3 as 3, this is the graph you are getting, and if you change your k value, you will get a different set of graph, right. So, that is how choosing this k value is a challenging task in construction of the KNN graph, but the process is very simple, very transparent. And there is another approach to construct the graph, that is the Epsilon neighborhood graph. So, which is called as Epsilon nearest neighborhood graph. In this Epsilon neighborhood graph, from every object what we do is consider this graph. So, I define the epsilon value, of course, this epsilon is also a predefined value, and I define a radius from this object. So, if I want to get the nearest neighbors from this node, then I define the epsilon value, and this is the radius of this object, and whatever the objects that are falling within that radius of epsilon, all those objects can be considered as neighbors, and to those nearest neighbors only I will be joining them, that is the edges will be available only between those nodes. And if you consider this object, and for this object the epsilon radius is this is the epsilon radius, and what are the objects that are falling within this epsilon radius, this one and this one. So, only for these two objects I construct the edges. So, similarly for this object, if you consider what is the epsilon neighborhood, maybe something like this, and here only this object I am having the nearest neighborhood. So, that is how the epsilon neighborhood graph can be constructed. So, here the problem here is you can somehow avoid the outliers, but in case of the KNN, no, so there is no way to avoid the what you call the outliers, but here also defining this epsilon value is much challenging. What is the suitable epsilon value is a challenging task. In case of the KNN, choosing that k value is challenging. And let us see what are the steps in the graph based clustering. So, once we have the construction of the graph, so because basically the clustering we are discussing is based on the graphs. So, that is how we should design the graph. So, we started with assuming that all the data objects are forming as nodes, and the distance between the data objects are the weights in the graph, and instead of having edges between every pair of nodes, we will be reducing the number of edges by choosing the neighborhood concept. Either the KNN neighborhood I can follow, or otherwise I can use the Epsilon neighborhood approach. So, using either of these approaches or some other approach, we construct the graph. So, once the graph construction is done, so we can proceed with the graph clustering. So, let us see what are the steps that can be followed for this graph clustering. The first and foremost step is construction of the minimal spanning tree. So, because we are discussing the clustering technique that is based on the MST. So, first we need to, so given this graph, assuming that, so given these set of objects, so this is the graph that I constructed either by using the KNN or by using the Epsilon neighborhood, then this is the resultant graph. Once I have the graph, then I need to apply the minimal spanning tree. The first step is the getting the minimal spanning tree. So, we know how to get the minimal spanning tree, right. So, in our third semester of BTech, we have discussed minimal spanning tree as part of the data structures course. Either you can use the Kruskal's algorithm or the Prince algorithm, any of the approach you can use and get the minimal spanning tree. So, once you get the minimal spanning tree, then you delete the branches iteratively, and of course, there are some set of techniques to delete these branches. So, here in this thing, so deletion of the branches is more complex. So, once your deletion of the branches is iteratively done, so at some point you will be stopping the based on the convergence criteria. So, then all the remaining, in the remaining graph, each connected component in your graph will form a different cluster. So, here basically these are the 3 steps that need to be followed. Once the graph is available to you, given the graph, then you need to design the minimal spanning tree. So, once the minimal spanning tree is available to you, so then you just delete the required branches. So, we will see shortly what these techniques that can be used to delete the branches. So, use some technique to delete the branches. So, once the deletion is over, each connected component in your graph will form the cluster, a single cluster. So, this process is very simple. We know we can use the Prince or the Kruskal's algorithm to get the minimal spanning tree, and once the deletion is over, then getting the connected components also we know, we discussed that as part of the data structures course. Then the typical process here is the deletion of the branches iteratively. So, how do we delete the branches iteratively, that we need to discuss in detail. So, consider this example. This is the graph which is constructed with this set of given objects. Then this is the minimal spanning tree that we derived based on this graph. So, once that is done, assuming that I am deleting this branch, so depending on some technique, following some of the available techniques, then this is the resultant graph. If you observe here, you can notice that this is one connected component and this is another connected component. So, now these 4 objects are forming one cluster, these 4 objects are forming another cluster. So, that simple it is to apply the graph based clustering on the given data set of objects. It is much intuitive, right. So, now let us see how do we delete the branches. The most tedious part in the graph based clustering is the deletion of the branches iteratively, and for deletion of the branches we have 3 different techniques. One is delete the branch with the maximum weight, or delete the branch which is of inconsistent. So, you can alternatively use the name branch also, branch or edge, both refer to the same in this context. So, delete the inconsistent branches or delete the edges with the analysis of the weights. So, we will discuss each of these techniques in detail in this lecture. So, now let us start with deletion of the branches based on the maximum weight. So, how do we delete the branches based on the maximum weight? So, in this stage what happens is, so whenever you delete the branch, so given this graph or the minimum spanning tree. So, on the minimal spanning tree only we need to apply this deletion of the branches, right. So, given this minimal spanning tree, at any stage if you remove one of the edge which is of maximum weight, so that splits the single cluster into 2 separate clusters. So, in every step if you delete one edge, so it gets you 2 new clusters instead of one single cluster. And the process we are following here will be the deletion of the maximum weight, and we need to repeat this process until we reach the required number of clusters. So, now let us see, this is the minimal spanning tree graph that is given to us. So, on the given graph this is the minimal spanning tree. So, you can observe the edge weights. We are going to remove certain edges with a maximum weight, and the approach that can be followed is, so you simply arrange the edge weights in the descending order. So, now they are in the descending order. So, 6 is the maximum weight, then 4, so it is the next highest edge, so on and so forth. So, that is how I arranged all the weights according to all the edges according to their weights. So, once that is done, you need to delete. So, now how many clusters are here available in your data? Only one cluster. If I want 2 clusters, then you just proceed. So, you know that there are there are many clusters, more than one cluster. So, you need to proceed and delete the highest weight edge. So, which edge you will be removing? So, the edge with highest cost, that is 6. So, now when you remove this edge, then what happens is these are all the objects that form one cluster and these are all the remaining objects that form another cluster. Now, you have 2 different clusters. So, this is how you, by removing an edge from your minimal spanning tree, you can get 2 different clusters. At any point in time, if you remove an edge, your single cluster. So, if you have one cluster or one connected component, that will be split into 2 different components. So, now this is one cluster, also one connected component, and this is another connected component which forms another cluster. So, if I know that, or if it is enough to get 2 clusters from this tree, then you can stop the process here. Otherwise, if you want to further cluster, get more clusters from this data, then you can proceed in the process and get more number of clusters. So, if you proceed to the next step, what is the next maximum weighted edge? So, that is 4. Now, this edge you need to remove. So, if you remove this edge, so this will be, so this single cluster, it will be split into this cluster and this cluster. Again, you are forming 2 different clusters, right. So, 2 different clusters will be formed when you first you deleted this, then the next highest you deleted this. So, that is how you can form. So, like 1 cluster, 2 cluster and the 3rd cluster. So, you have 3 clusters now. So, if it is enough for you, you can stop the process here, or otherwise you can proceed and continue to get more number of clusters. That is how you can repeat the process to get the required number of clusters in the case of the deletion of the weight with the maximum weight. And the next approach to deletion is you can follow the inconsistent edge. So, you identify the branches or edges which are inconsistent. Remember, branch and edge are alternatively used in this context. So, you can remove a branch or edge which is inconsistent. So, you can define the inconsistent edge this way, inconsistent edge this way. So, if you consider any edge E and its weight dE is greater than the reference value dE complement. So, here dE complement is the reference value. We will see shortly what the dE complement is. So, any edge or branch can be called as the inconsistent edge if the edge weight dE is greater than the dE complement. Now, let us see what is this dE complement is. So, dE is simply the weight of the edge, but what is this dE complement? This is known as the reference value. And how do we get that reference value? The reference value can be defined as the average weight of all the edges associated with that edge. Now, consider this edge. So, this edge is E and the edge weight dE. So, this is dE equal to 6 because this is the weight that is given to it. And what is the dE complement? Let us try to compute the dE complement. What is dE complement? The average of the weights associated with this edge. What are the associated edges with this edge? So, at this end, whatever are associated, all those edges can be called as associated edges. So, once you know them, you take the edge weights of them. So, that is 1, 2 and 3. So, these are the associated edges with this edge. Now, you just take the average of that. So, what is the sum? What is the average? So, sum by the number of edges. How many edges are associated with this? 3. So, in the numerator you have 3 and in the denominator you have 3 and 1 plus 2 plus 3 it is 6. So, 6 by 3 it is 2. Now, dE complement you get this value. So, that is how you can compute the reference value for any edge. So, this is how you can compute for this edge. For the other edges also you can compute this reference value. So, I repeat, the reference value can be computed as the average weight of the edges associated with that with any edge is called as the reference value, and any edge is called as known as a inconsistent edge if its weight is greater than the reference value. Now, consider this case, its edge weight, its edge weight is 6, but its reference value is 2 only. that is edge weight is greater than, so 6 is greater than 2, so here it is 6 is greater than 2, that is you can call this edge as inconsistent edge. Maybe you can remove this to get the clusters. So now this forms one cluster and this forms another cluster. So that is how you can remove the inconsistent edges from the graph to get more number of clusters. So now another process. So far we have discussed two different approaches for deletion. One is removing the edge with the maximum weight. The other approach is removing the inconsistent edges in the graph. And now we have seen example for the removal of maximum weights, and shortly we will see the removal of the inconsistent edge example. So there is another technique also, another approach for the deletion, that is analysis by the weights. So you can analyze the graph, and by analysis of the weights of the minimal spanning tree, you get a threshold. And how do we get the threshold is, you just plot the histogram with all the weights of the branches. Assume, so for this minimal spanning tree, and this is the histogram that is formed. And once you plot the histogram for all the edge weights in the minimal spanning tree, and you can see somewhere there is a gap between the peaks, there is a valley, and here there is a gap, and that gap will act as a threshold, and that is how you can define the threshold yes. So once that threshold is identified, you can remove all the branches which are greater than this, whose weight is greater than this threshold yes, right. And if I remove them, so the resultant minimal spanning tree look like this, and this is the histogram. Now there are no more graphs, right. So that is, this forms one single cluster. So the connected components forms the cluster. So that is how you can form clusters in the graph based on the edge weight analysis method. And now let's see an example for how do we get the or delete the inconsistent edges to get the clusters. So this is basically the given graph, and we'll see how to find the minimal spanning tree of this given graph, and we'll see how to apply the clustering of the graph by deleting the inconsistent edges. So for this graph, so we know whether we can use the Prince algorithm or the Kruskal's algorithm to get the minimal spanning tree. Here you can see, you follow any of the process, so get this minimal spanning tree. So it's marked in green and I am now marking in red. So that's what the minimal spanning tree for this graph is. So these are all the edges in the black, they are the removed edges from the minimal spanning tree. So all the edges in the red, they are marked in red and green. They are the edges of the minimal spanning tree. We are not interested in the rest of the edges. They can be removed in the process. Now what is the next step once you get the minimal spanning tree? So once this minimal spanning tree is obtained, you have to identify the reference value, because you are using the process of identifying the inconsistent edges. So to get the inconsistent edges, you should understand the reference value. So if the edge weight is greater than the reference value for an edge, then you can call it as such an edge as a inconsistent edge. So let's try to identify that. So for this edge, 1 is the edge weight. So all the numbers marked in black, these are all the edge weights. So these are all the edge weights. And all the numbers marked in red, they are all the reference values. So how do I compute the reference value for this edge? So assume this is not available. Let's try to compute that. So how do you define that? The average value of the edge weights associated with this edge. So how many edges are associated with this edge? So with this edge, only one edge is associated, right? This side there are no edges, only one edge. And what is the average value of the weights of that? So 3, it's 3 by 1, right? Only one edge, that is with the weight 3 by 1. So that is how I get the reference value as 3. So it's equal to 3. So the reference value for this edge is 3. And is it an inconsistent edge first of all? So can you check that? How do I check that? So if the edge weight is greater than this reference value, then only we can call it as inconsistent edge. It's not an inconsistent edge, right? So you need not to remove this edge. You can retain this edge. So this is a proper edge. It's not inconsistent. Right? For your understanding, it's a consistent edge. Right? So now let's find the reference value for this edge. So what are the associated edges? This edge with weight 1, this edge with weight 5. So 1 plus 5 by the number of edges are 2. So that is 6 by 2, which is equal to 3. So that's how you get this reference value. And now for this edge, so the weights associated are this one and this one and this one. That is 3 plus 6. So 3 plus 6 by 2 edges. So 9 by 2 is 4.5. So 4.5 is the reference value. So that is how you proceed and identify the reference value for every edge. So now let me remove this. So I have given already the edge weights and the corresponding reference values. Remember, so all the numbers in the black, they are the edge weights. The numbers in the red, they are the reference values. So now you need to identify the inconsistent edges and you remove them. How do you get the inconsistent edges? If its edge weight is greater than the reference value. So for every edge you need to check that. So now 1 is greater than 3. So 1 is greater than 3, false. So it's not an inconsistent edge. Now here 3 is greater than 3, no, it's also false. So you can retain that. So here, so 5 is greater than 4.5. Yes, right, it's true. Now this is an inconsistent edge. So this edge has to be removed. And now here, so 6 is greater than 3.6. Of course, it's also true. So now you need to remove this because it's an inconsistent edge. Now let's proceed. So now 4 is greater than 4, it's false. So this can be retained. Now 2 is greater than 5, it's true, and you have to retain this edge also because it's not inconsistent. So only these two edges have to be removed. So if you remove these two edges, then so what are the clusters that we get? So this is one cluster and this is another cluster. And of course this is a single point, and you can consider that as a noise point because that's not part of any of the clusters. Right, so that is how we get, and assume that, so if these are the edge weights, then that's how we get, and assume that this edge weight is 6. Then what happens? If the edge weight is 6, then in that case this edge also becomes a inconsistent edge and this edge also has to be removed. Now this becomes another cluster. So now if you have that edge weight, so to A and B is 6, then so this is one cluster I get, this is another cluster I get, and if you observe, these 2 points are not part of any of the clusters. So such points are called as the noise points. Right? So this is the process that we follow to get the clusters in case of the graph based clustering by following the minimal spanning tree based clustering, where the deletion approach that we follow is that inconsistent edges are getting deleted iteratively. And because I want 2 different clusters, so I stop at this process. So if you want more number of clusters, you repeat the process and then delete one more edge. And just to summarize, in this class we have discussed what graph based clustering is. So basically we need to construct the graph to apply the graph based clustering. So how do we construct the graph? So all the nodes, all the data objects in the data set, they form as the nodes in the graph. Then all the distance between the data objects, they form as weights in the graph. That's how we construct the graph. And also you can even apply the KNearest Neighborhood or the Epsilon Neighborhood approaches to define the neighborhood in the graph, so that we can reduce the number of connections in the graph, thereby you can reduce the complexity of the computational complexity of the process. So once the graph construction is over, then the next process is you need to apply the minimal spanning tree, get the minimal spanning tree. So once you get the minimal spanning tree, on that you need to iteratively remove some of the edges, and to delete the branches or the edges iteratively, you have 3 different approaches. One is removal by maximum weight, the other is removal by inconsistent edge. So one more technique is removal by analysis. So that's what we have discussed so far in this class, and these are the steps you can follow iteratively. So that's why I am calling it as hierarchical method. There is nothing to do with the hierarchical clustering. And in the next class we will see how to visualize the data sets, the large data sets or the small data sets. So how do we do the information in the large data sets. Thank you for watching the video.